While the physics of antenna resonance can be visualized like a tuning fork, the underlying engine of radio theory is complex algebra. But you don't need to be an expert in maths to use these formulas. But you need to understand three core mathematical concepts: the imaginary unit J, the impedance equation, and the reflection coefficient. Actually, the imaginary unit is I, but in electrical discussions, as it is likely to be confused with current, J is used instead. It is the square root of -1. If any real number is multiplied by it, the product is an imaginary number. Let us go back to our higher secondary school days and recollect the equations. Practical measurement using the nano VNA is also illustrated, which of course is more important for the amateur radio operator. In a direct current circuit, resistance is symbol R. In an alternating current circuit, like radio, we use impedance, which is a complex number, also called a 2D number. Z or Z, the impedance, is equal to R, the resistance, plus J into X. R is resistance, the real part, energy that is actually radiated or turned into heat. J is the imaginary unit, square root of -1, as already mentioned. In radio, it represents a 90-degree phase shift between voltage and current. It means that voltage and current do not rise and fall simultaneously when there is inductance or capacitance, unlike in a purely resistive circuit. There is difference in timing by 1/4 of a cycle period. One full cycle is 360 degrees. So 90 degrees means quarter. X or reactance is the imaginary part, that is energy stored in magnetic or electric fields but not radiated. Inductive reactance XL is equal to 2 pi FL, that is it increases with increase in frequency. XC is equal to 1 by root of 2 pi FC. So capacitive reactance decreases with frequency. Resonance is the specific mathematical state where the imaginary parts cancel each other out to zero. So at resonance, the inductive reactance XL minus capacitive reactance XC is equal to 0. When this happens, the equation Z or Z is equal to R plus JX simplifies to Z equal to R plus J0. That is just R. The antenna looks like a pure resistor to the radio. Mathematical result is that voltage and current are perfectly in phase. As we discussed earlier, there is no 90-degree phase shift. But even if Jx0, R could still be a definite value, 10 ohms or 500 ohms. So resonance doesn't mean it is 50 ohms. It means it is purely resistive component. So if the impedance or the resistance, purely resistive component, does not match that of the radio, there will be standing wave and SWR will be high. That brings us to the math of impedance matching or SWR. Impedance matching uses the reflection coefficient gamma, capital letter gamma, to see how much energy bounces back from the antenna because the load impedance doesn't match the source impedance, that's the radio, usually 50 ohms. Gamma is equal to the difference between load and source impedance divided by the sum of load and source impedance. The standing wave ratio is then derived from the magnitude of that reflection coefficient gamma. SWR is sum of 1 and gamma divided by difference of 1 and gamma. So from the equation, if the load impedance, that is the antenna impedance, is 50 ohms, then gamma is 50 minus 50 divided by 50 plus 50. Anything divided by 0 is 0. Then SWR is 1:1 as per the above equation. Perfect match. If the load impedance or the antenna impedance is 10 ohms, it can still be resonant. But gamma or reflection coefficient becomes 10 minus 50 divided by 10 plus 50, which is minus 0.66. Then by the above equation, SWR will be 5:1. Even though it's resonant, the math says the match is terrible. Something similar to that occurs in a multi-element Yagi antenna. As the number of elements increase, the impedance of the resonant dipole radiator decreases from the typical 70 ohms of a dipole to a low value. That is why you use a gamma match for Yagi antenna. Now let us summarize. At resonance, total reactance is 0. So the antenna acts like a pure resistor with no reactive power. Impedance match is load impedance is equal to source impedance, that is matching of antenna versus radio. So there is no reflection, maximum power transfer. Our perfect combo will be load impedance is equal to 50 plus J into 0, that is just 50 ohms. Maximum efficiency and no reflections. That is what we have for a well-tuned antenna, as illustrated in the picture, almost fairly okay. Let me hope that anyone with a minimal knowledge of mathematics up to the higher secondary school level would have been able to follow the discussion.